Hello world, it's Rahul. Welcome back guys to machine learning tutorial, and today we're going to see mathematics intuition behind support vector machine. So guys, I have discussed basic intuition of support vector machine in my previous video, including hyperplane, margins, marginal distance and logistic regression versus SVM. If you haven't watched that yet, then I'll suggest you to first have a look into that so that you'll have an idea about support vector machine. I have attached the link into the description of this video. So guys, today we'll see how mathematically we can derive support vector machine and its attribute. So guys, before starting this session, let's first understand about some basics of linear algebra. So if you can see the Cartesian, let's draw a line from the origin, and this is nothing but the vector. So vectors are mathematical quantity which has both magnitude and direction. So in this case, vector is having upward direction. So we can consider it as some positive value with a magnitude or length between origin and the point. So I can draw various vectors like shown on the screen. Okay, so now suppose we have a vector with value of x as 3 and y as 1. So we can represent it as y is equal to 3, 1. Now let's say if we have to calculate the length of this vector, as we know that every vector has some length and direction. So the length of this vector x is called its norm, which is written as norm of x is equal to under root of x square plus y square. So here x is 3 and y is 1. Let's substitute this value in equation and we will get the length of a vector as under root of 10. Now we have to calculate the direction of this vector. So for that we can write it as w is equal to x upon x magnitude and y upon y magnitude. And if you look at the plane shown on the screen, you can see that cos theta is equal to x upon x magnitude and cos alpha is equal to y upon y magnitude. Thus direction of this vector can also be written as w is equal to cos theta, cos alpha. So guys, these things will help us to understand and solve the classification problems using support vector machine algorithm, which we will use later. Now we have dot product of two vectors. Let's say here we have two vectors x and y as shown on the screen, and we have to find out how these two vectors are related with each other. So the formula for finding dot product will be norm of vector x into norm of vector y into cos theta. Now by looking at the figure as shown on the screen, we can see that theta is equal to beta minus alpha. Then we can get cos theta is equal to cos beta minus alpha. So guys, just to add one thing, that cos a minus b will be cos a cos b plus sin a sin b. Now if we substitute this into the dot product formula, then we will get it as x1 y1 plus x2 y2. So guys, in SVM we have to create a hyperplane that gives us zero training error. So what is the best boundary is the question. So let's first understand the line. Let's say our data is in 2 dimension, and if we have this line, essentially what this line is doing is dividing the space into 2 parts. So we can express this line as y is equal to mx plus c, as we have seen in earlier cases, and we can rewrite it as w1 x1 plus w2 x2 plus b is equal to 0, or w transpose x plus b is equal to 0. And if I create a perpendicular line to this hyperplane, then it will be represented as w vector is equal to w upon norm of w, and distance of this hyperplane from origin will be minus b over norm of w. That means if you don't have b, then this part will be 0 and your line will pass through origin. So guys, till now this was some basic intuition about linear algebra, which we will use once we start solving or optimizing the equations for support vector machine. Now we have data scattered on the Cartesian plane with hyperplane separating two classes as shown on the screen. Let's say blue points are considered to be negative class and red points are considered to be positive class. Now suppose if I have to check for a new unknown data point whether it belongs to positive class or negative class. So we have three cases over here. If W transpose X plus B is equal to 0, that means new point is on the hyperplane, as this is satisfying the equation of straight line. Now case 2 will be if W transpose X plus B is greater than 0, then point will be above the line, or we can say that it is in the same direction of unit vector what we have seen earlier. And last case will be if W transpose X plus B is smaller than 0, then new point will be below the line, that is categorized as negative class. Now if I know these conditions and want to classify any new data point, then sign of W transpose X plus B is what we need to find out. So here we want magnitude of the value to be large, or in other words, if I know the label of my outcome, then I can say y of W transpose X plus B should be large. So why did I do this is simply if it is positive point, then y will be plus 1. Then we want W transpose X plus B value to be large. Or if it is negative point, then both y and W transpose X plus B will be negative. And once we will multiply these values, it becomes positive. So in general, for any point, we want y into W transpose X plus B to be large. Now it is necessary to understand over here that we want this value to be large, but with correctness of it as well. Now let's talk about margin, as we have seen how we can draw hyperplane for separating the two classes, because in SVM, our job is not restricting till drawing the hyperplane. We have to draw margin as well with maximum marginal distance. So guys, margin is nothing but the distance between hyperplane and the nearest point. Let's see how we can derive the margin for both positive and negative classes. Now let's say we have a line with unit vector W perpendicular to this line. Now let's consider a point X in positive side and draw a projection of it on the line, that is X hat. So now we have this vector X and this vector is X hat, and let's denote the projection as P vector. Now I can write P is equal to X minus X hat. So we can clearly see that X hat is lying on the plane, so the equation for that will be W transpose X plus B is equal to 0. Now what is P? So P is a vector which is perpendicular to this line, which means that P is parallel to unit vector W. Now let's assume that magnitude of P be that margin gamma. That means P is nothing but unit vector W times gamma, and that is equal to gamma times vector W over norm of W. Now if I substitute this value into P is equal to X minus X hat, then X hat will be X minus W vector times gamma over norm of W. Now let's replace X hat in equation W transpose X plus B is equal to 0. We will get gamma as W transpose X plus B over norm of W. Guys, just to add one thing, W transpose into W vector will be square of norm of W. If X is below the line, then margin value gamma will be minus of W transpose X plus B over norm of W. So guys, by getting this knowledge, one can create margin. Now if you know the label of new unknown data point, then this will become as y times W transpose X plus B over norm of W. Now we can compute margin for every data point, but here we cannot maximize everything. So what we will do now, we try to maximize the margin with respect to closest point to our hyperplane. Let's say we have a Cartesian plane with positive and negative points scattered, and whatever hyperplane we draw, we consider the points that are closer to it and try to maximize that. So this is the whole idea of margin. Now, if we have hyperplane and margin line with us, then the equation of hyperplane will be W transpose x plus b is equal to 0, as I told you earlier. And the equation of line that parallel to our desired hyperplane and goes through the closest positive point will be W transpose x plus b is equal to 1. And the equation of the line that parallel to our desired hyperplane and goes through the closest negative point will be W transpose x plus b is equal to minus 1. So guys, we have just find out the gamma value for positive point as W transpose x plus b over norm of W. And if we see the equation for positive margin line, then we can equate that W transpose x plus b is equal to 1. So that our positive margin distance from hyperplane will become 1 over norm of W. Same we can apply on negative margin distance from hyperplane, as negative margin line is having an equation of W transpose x plus b is equal to minus 1. And if we put this knowledge into gamma value for negative point, then that will also become 1 over norm of W, as margin is negative and W transpose x plus b term is also negative. So whole will become positive. So guys, by adding these two margins, we will have complete marginal distance for this SVM problem. And that will be 1 over norm plus W plus 1 over norm plus W equal to 2 over norm plus W. So this is what we want to maximize. So guys, if I minimize the norm of W term which is present in the denominator, automatically it will maximize the margin. So let's flip this margin term and minimize this complete function. But we also ensure that data is correctly labeled by looking into the constraints such that y times W transpose x plus b is greater than equal to 1, as this quantity will be greater than equal to 1 only if all the points are on the right side of the line. Now for minimizing the norm of W, we must have to use any optimization technique. But one thing to note here is that we are not going to use gradient descent over here. And why we can't use gradient descent? For that, first let's understand what type of function we are going to optimize here. So in linear regression and some another algorithms where we were using gradient descent, simply we were maximizing the W transpose x plus b term for reducing the error. But here we are assuming it as a constraint. So it is slightly different than the optimization function or formulation what we have seen earlier. So earlier we were looking onto unconstrained optimization. We just had an objective function and we were trying to find the value. That's why we can't use gradient descent over here to solve our equation. So guys, for solving this equation, we need quadratic optimizer, as we have to minimize the square of norm of W over here, which is not linear anymore. So guys, still we are looking for linearly separable data. Whatever we have studied till now will apply only on linearly separable data. So guys, that's it for now. In next video, we will see how we can optimize this function using quadratic optimizer, and we will derive the function mathematically. And we will have a look into non-linearly separable data as well, like how we can solve those problems by making use of kernel trick. Thank you guys for your time. Do like, share and subscribe. Hit the bell icon to get the latest updates. Happy learning and stay safe.